Hi, so today I am teaching 5.1 trusses, method of joints, and method of sections. Okay, so I have the joints here and sections here. They find the same thing, but they are a little bit different methods of getting the same answer. I like joints better just because you can literally do it on any sort of truss. Sections you need, you can only find certain members depending on where you place the cut, and I'll explain later, but joints I like better, so I'm going to do that first. And so what you do is, these are all joints. Okay. Well, first of all, what we're trying to find is this is a truss. Okay. This is a structure. It's got 225 Newton force going directly up at point A, and it's got a 450 Newton force going directly left at point D. And there's a point C right here, by the way. All of them have color except point C. But what's happening here is this truss, it's connected to ground right here. Okay, and it's pushing on the ground right here because of this Newton force. It's getting pushed like this, and so the ground is pushing up 225 newtons right there, which that doesn't really matter. It doesn't really matter where the ground and all that junk is. It'll help with the context of the problem, but for the math, you don't need it. You don't need to know that this is connected to ground and this is pushing on the ground. All you need to know, this is the free body diagram of our structure. Okay, and so what you do, right, is you look at every single point. Okay, you look at A, you look at B, you look at C, and you look at D. Those are the 4 points on this truss structure. And so you want to start with a point that has the least amount of unknowns and the most knowns. Okay, so B has 3 unknowns. We don't know anything about AB, BC, or BD. C, there's 2 unknowns, no knowns. D, there's a lot of stuff going on with D. There's 3 unknowns and there's 1 known. But A, we're going to start out with A because A is it's simple and we can find stuff with A. And so the free body diagram of A, here's point A. Okay, here's the 225. And so there's 2 trusses that come to point A, right? And one of them can affect the Y direction, and it's this one. Okay, because we know A is at equilibrium, it's not moving. And so we have to counteract this 225. And so this beam doesn't move at all in the Y direction. It's perfectly horizontal. It doesn't move at all in the Y direction. So this one has to be going down to counteract this 225 that we know is going up. And so now this doesn't have an X direction, and this does. So we have to counteract that X direction like this. And so those are the directions of these arrows. Okay, of the free body diagram of point A. We're going to call this force from A to D. And we're going to call this force from A to B. Okay? And so we can sum the forces in the Y to get to find what AD is. And well, we're going to sum forces in the X to find FAB, but if we sum forces in the Y, we'll be able to find FAD. And so there's a positive 225, right? And using the geometry of the truss, okay, this truss right here from A to B is 4 meters, and this truss right here from B to D is 4 meters. So we know that this is a 45-degree angle. These both are. And so it's minus because it's going down. Okay, we're going to calculate the Y of this force of FAD. So it's going down to counteract the 225, and we're going to do this angle right here. So the cosine, right, of 45 times FAD is the y component of FAD. And so I was very brief with finding that y component because we've explained it before in other videos. You can look in my statics folder, the playlist, and find other videos, numerous other videos that'll explain what I just did there. But all you need to know is that this is the y component of my FAD, and it's going down. That's why it's negative. And so when you do this math, you calculate that FAD is equal to, we can sum the forces in the x. Okay, so we have a negative FAD. Right? The FAD is going this way. It's negative, and the magnitude of that force is the sine of 45 times our 318. Okay. The second term here is our FAB. Okay, and so when you solve that, your FAB equates to 225, I believe. Yeah. And so just by looking at point A, we found FAB from A to B, and we found FAD, the force from A to D. Okay. Now let me teach you another thing. There's this concept, compression and tension. Okay, those are some terms that we have to know when talking about method of joints and method of sections. Compression. Okay, so when you look at point A, right, the 225 is in compression. Okay, it's going towards the A, right? It's compressing it. Same goes for the FAB. FAB is in tension. It's pulling on it. Okay, that's what it is when you look at A, and that's how you should view compression and tension. So it's safe to say that FAD, right, is in tension. Or no, I'm sorry, compression, and FAB is in tension. Okay, because the FAB is pulling and FAD is pushing on point A. Okay, so now since we know FAB, right? We can use it to figure out the. We're gonna look at the free body diagram of point B next. Okay, because there's the least amount of unknowns there, and we can use it to find DB as well as BC. So point B is going to look like this. Okay, so I just drew the free body diagram of point B. Okay, and so I started with this 225. We know FAB, is 225, and it's going this way when you look at A. Right, so this beam, it's going this way, which means there's equal and opposite force over here. Okay, so these forces, it's either the forces across a truss are they're either like this or they're like this. Okay, that's a really bad point, but this is better. But in this case, the 225s are going like this. Right? They're in equal and opposite directions of each other and forces. And so that's why this arrow is going left, which means this arrow, and we know B is at equilibrium, which means this arrow is going right. Okay, and so we're going to start with the y's, which is pretty easy. So we know B is at equilibrium, it's not moving. So these two forces over here are perfectly horizontal. There's no y component. The only y component in this free body diagram is FBD. It's in the positive direction. And we know that it's in equilibrium, right? It's not moving. So the sum of the forces in the y direction is equal to 0. Okay? That means FBD is 0, because it's the only one in the y direction in our free body diagram. So that one's pretty simple. If you sum the forces in the x, okay, we get a negative 225 and a positive FBC equals 0. Do a little math and you find that FBC is 225 newtons. And it is in tension. Right? Because it's pulling away from B. And so now we have AD, we have AB, we have BD, and we have BC. All we need now is CD. And the way that we're going to do that, we're going to draw the free body diagram of D. Okay, so what I just did, I drew the free body diagram of point D. This is the 450 newtons acting on point D to the left. This right here is the 318 newtons, the FAD, right? It's equal and opposite. Right? See how this one is in compression, and this one is also in compression. FCD is, we know that FCD, that's the one that we don't know, right? But we know it's going that direction, it's in tension, because we know the two directions of these two forces, right? And there's some Y force, right? This doesn't have any Y component, but this does have a Y component, and it's going up. And so we have to counteract that component, because we know that D is at equilibrium. Okay, and so it has to have a negative Y component. FCD does. That's why it's going down. And so this is pretty simple. You can sum forces in the Y or the X. We're going to do it in the Y, or the X, I'm sorry. So the X component of our 318 is a positive. We can use this angle. Cosine 45 times 318. Okay. And FCD is also a positive. Again, it's got a 45-degree angle, so it's going to be cosine as well. Cosine 45 times FCD. And finally, our 450 is in the negative direction. Okay. So that all equals 0. Do a little math. We only have one variable. The FCD is equal to, I believe, 318 or 225? 318 newtons. Which makes sense. And it is in tension, because it's pulling away. Okay, so now we have FAD, we have AD, we have AB, we have BD, and BC, and CD. We have every single member in this truss. Oh, and BD. I said BD. We have every single member in this truss. And that's method of joints. Okay, I'm going to do the same problem with method of sections. But what happens with the method of sections? You don't look at the joints. Okay, you look at a section. So you cut, right? You cut the member, and then look at one half of it. Okay, so usually what you do is you look at the half that doesn't have ground. This is our ground, I said earlier. So we're going to cut it right here. We're going to look at that side. The problem with sections is you cut right here, but you have no idea what the force in this member or this member is. If you cut right here, you can only find the forces of CD and BC. And so that's why I like joints better. But I'm going to redraw here. Okay, so I just redrew this structure, except I cut this structure here, except I cut it off at these two members. And I drew in two forces for at those members for what their internal forces are. We know what we're going to do is we're going to sum the forces in our picture. Simple as that, in the x direction and the y direction. And so we know it's at equilibrium, okay? It's not moving. So our 225 is going up, which means we have to go down somewhere. That's where the FCD comes from. And our 450 is going left, which our FCD, if it was strong enough, it could potentially move it as well. But we're going to put FBC in the right direction as well, because it makes no sense to put it in the other direction. Which if we did put it in the other direction, we just get a negative number, which means it goes in the other direction. I know which direction it is, so it's a lot easier for me to predict. But if you get it wrong on your prediction, you're just going to get a negative number, and the math will help you out. It'll tell you which direction it's going. And so we'll start with the y's. Okay, we have a positive 225. We have a negative sine 45 of FCD. Okay, that gives us, when we do that math, believe it or not, that gives us 318 newtons in tension. Okay, so what I did here, some forces in the x, and some forces in the x, some forces in the y. And I found FCD as well as FBC. Got both positive numbers because I know which direction the arrows are going. And by no surprise, FCD 318 is the same as as the number we got when we did it in joints. And FBC is the same as the number we got when we did it in joints. So you can do it either way, right? You can find the forces of the members with method of joints or method of sections. I like method of joints better, but they both work. So here's the proof. But that is all.